right, boys and girls, today is the final day of our review. Tomorrow is, of course, your final exam. It is a 90-minute exam. We'll start at 8 a.m. You will have 90 minutes once you begin it to finish, which should give you a little bit of extra time at the end of class, 7 or 8 minutes, to go back through anything you may need to make sure you've turned in, right? Give you some time when you're done to do that. That being said, tomorrow is the last day of this class for the remainder of the semester. You are required to be in the room during class time between now and final exams. You are welcome to bring anything to study for that exam, and you are not allowed to leave the room, right? So there's no running to the cafeteria for a soda, there's no, hey, can I go speak to so-and-so because I know they have a free period, none of that, right? So plan accordingly to be studying for your other final exams for those 3 days that we are in class. All right, so I'm gonna go back to chapter 9 and go over the molecular geometries and electron geometries, as well as bond angles and hybridization of each of the different 3 types that you need to make sure you know. The first is, of course, going to be the electron domain geometries. This is going to be based on bonding and non-bonding domains. Do we remember what that means? If something is bonding, there's a bond. If something is non-bonding, it's a lone pair. That's what that means. We're going to start with 2 bonding, 0 non-bonding. This is, of course, going to have the geometry of linear electron domain geometry. These look something like a central atom with 2 things bound to it. Those things bound to it can be lone pairs, or they can be actual atoms, okay? Remember that we always draw and we talk about this from the perspective of something that has a central atom. Whatever atom we are looking at and defining as the central atom is the one that we use to determine geometries. The linear electron domain geometry, the term linear is, of course, its geometry, all right? The molecular geometry if 2 things are bonding and nothing else is non-bonding, is linear. If 1 and 1, still linear. Our bond angle, 180 degrees. Always 180 degrees. Our hybridization, always based on the electron domain geometry. For this one, is going to be SP. All right, let's move on to our next situation. 3 bonding domains, 0 non-bonding domains, and everything underneath it is going to be a trigonal planar molecule. This electron domain geometry applies to any molecule that has 3 domains, whether they are bonding or non-bonding. It's going to be a trigonal planar molecule as far as the electron domain geometry is concerned. From there, we can talk about what happens. When we have bonding, non-bonding. That's what these numbers mean. Make a note. Bonding / non-bonding. Bonding number on the left. All right? When 3 things are bonded and there are no non-bonding pairs of electrons, we have a trigonal planar molecule. Remember that molecular geometries only take into account the atoms that are bonded. They ignore the lone pairs, but the lone pairs still affect the shape of the structure. 2 and 1 is going to be a bench structure. 1 and 2 means there's only one thing bonded to the center atom. What's that one? Linear. Remember, we stopped doing anything after 1 because of the fact that they're all going to be linear at some point. Okay? The bond angle for something that has 3 bonded atoms, 120 degrees. For something that has 1 lone pair, remember that the lone pair affects the other atoms by pushing them away from itself. All right, our last one is tetrahedral. Oh, oops, did I forget this? Hybridization based on the electron domain geometry, 3 things, sp2. All right.
You want us to know trigonal bipyramidal and octahedral?
No. Remember we talked about that. Tetrahedral item has 4 things bound to it, whether they are pairs or atoms. The electron domain geometry is going to be tetrahedral. The hybridization of a tetrahedral molecule will always be sp3. From there, we can identify the molecular geometries. When all 4 things are actually bonded, what is the molecular geometry? Tetrahedral. What's up?
Yes, we won twice.
Oops. When 3 of these things are bonded, and 1 of them is a lone pair, that lone pair pushes everything else down and causes a trigonal pyramidal structure. That was today's daily Q. The molecule NH3 is tetrahedral, electron domain geometry with a hybridization of sp3, and a trigonal pyramidal molecular geometry. 3 things that are bonded, 1 that is not. 2 and 2 is going to be bent, and 1 and 3, like we just talked about, at some point they all become linear. What is the bond angle in a tetrahedral molecule that has all 4 things as bonded atoms? 109.5 degrees. What about in these structures? Less than. What is the bond angle in a linear structure always? 180. You are unlikely to come across something like this. Or that. So that covers all of that chapter 9 stuff that we talked about yesterday. Yep.
Is the bent also the 109.5?
Less than 109.5. Yep. All right. Moving on to chapter 10. We covered the rest of chapter 9, correct? Okay. Chapter 10 was very heavy in the equations. Chapter 10 was all about gases. Some of it was review. Some of it was not. I would say PV equals nRT was pretty much review. The gas laws that led to the ideal gas equation was also review. The first few sections talked about Boyle, Charles, and Avogadro. Boyle related pressure and volume and said that they were inversely related. Charles related volume and temperature. T being in Kelvin. Said that they were directly related. Avogadro related volume to moles. Again, directly related. We use these in a very specific way. Okay. We had some initial final situations where the ones meant starting and the twos meant ending, or initial and final, if you will. And we could relate any of those different situations in order to come up with a final answer. If volume and moles we started with, and we wanted to know how many moles we would have based on the change in a volume, then we could calculate that using Avogadro's law specifically. So those were the mathematical versions of those laws. From there, we got the ideal gas law. You know this one, you've seen this one several times before. R is the constant based on the units that you should be using. Pressure should always be in what unit? ATM. Volume should always be in liters. N should be moles. T should be Kelvin. As long as you are continuing to hold fast and true to these specific units for the gas laws chapters, right? Make sure you are converting. If you are given in Celsius, convert to Kelvin. If you are given in milliliters, convert to liters. Yes?
If we have like an ideal gas, how would we give us the R?
I would say the only R you need to know, write it down, is this one. The unit is liters ATM per mole Kelvin. The reason this is the only R you need to know is because you will convert everything else before you plug and chug.
Okay.
Does that make sense?
Mm-hmm.
We're very specific about this. There were a ton of different R values that you could have used in that chapter. It gave you R values for various different units. We're using those 4 units, always, for the ideal gas law and for Boyle, Charles, and Avogadro. Yes?
So, do you want us to try to remember some of the pressure conversions, like torr and stuff like that?
The big one
So,
is the 760 equals 1 ATM. I would say that's pretty much the only one you'll ever need. And they're identical, right? That's the only one I would say you really need to worry about. I don't think I gave you any like pressure related problems, but I'll go back and double check. Pressure conversions are small potatoes compared to some of the other concepts I'd rather test on. All right. When are ideal gases when do gases behave this way? Remember this? Low pressure, high temperature. It's a T. Also known as the environment we live in. Low pressure, high temperature. Outside of that particular environment, we have to do what we call deal with real gases. So we introduced something called kinetic molecular theory. Kinetic molecular theory was a good way of describing how gases behave to create the environments that they prefer, like pressure. There were postulates. I believe there were 5 postulates of kinetic molecular theory. There were ones that stated the obvious. Constant, random, or chaotic motion was the first one for kinetic molecular theory, gases. The volume is negligible, specifically compared to the container they are in. In other words, the volume of gas in this room, whatever type of gas it might be, is going to be negligible compared to the size of the room itself. Most gas takes up takes up no space, right? The next one involved attractions. They do not attract or repel each other. They just basically don't interact, was one of the KMTs. Yeah. The last one says that the kinetic energy of the molecules is proportional to the temperature of the molecules, which is something we've talked about several times in the past. Okay. So, deviation from an ideal real gases do collide and experience attractions and repulsions. That's the first one. The collisions with the side of the container are mostly responsible for the pressure. It was something kind of postulated, but it is the real behavior of our gases that we have to concern ourselves with. Yeah. When we talk about real gases, the real situation is that they do collide with each other. Sometimes they stick together. Sometimes they repel each other. When they repel each other, they may be moving faster or slower. The last one is that kinetic energy is an average. Every molecule has its own amount of kinetic energy, and that amount is going to be averaged across all molecules, right? So if we stuck a thermometer on top of my tissue box right here, and we took the temperature of this room, we could figure out how fast the molecules are moving, because we can relate kinetic energy to temperature, right? Is the temperature of the gas that is up on my desk going to be the exact same as the temperature above my heater? Absolutely not. The real situation is that we take an average temperature of the entire space and we say this applies to everything, right? But it's only because the actual situation is too complicated to handle. If we wanted to, we'd have to put a thermometer in every inch of this particular room to know the actual situation. Are we going to do that? Probably not. Yes?
So you're saying that the kinetic energy is average?
Yep, kinetic energy is average.
Okay.
Not really the case. Right? Does that make sense? Okay. A couple of other concepts from chapter 10, Dalton's law of partial pressures. Dalton states that the total pressure of a system is equal to the sum of all of the pressures of all the gases that are present. One of the ways that you were asked to do problems with this was you're told, okay, there's a mixture of gases that are being held at STP. Okay, so what does STP mean again? What is the standard temperature? What did you say?
200.
Okay, the standard pressure is 1 atm. What is the standard temperature? 273.15 Kelvin, also known as 0 degrees Celsius. Oh boy. Cool. Mixture of gases held at standard temperature and pressure. If we know that there are 3 grams of CO2 and 4 grams of O2, what can we do with that information? Can we calculate pressure given all the information we have? Heck yeah, you can. You can do that for each of the individual gases. Once you know the individual gases, can I figure out what the total pressure is? All I gotta do is add them together. What do we have to do with this information before I can use that ideal gas law? Convert it to moles. See why I said I'm probably not gonna give you a straight up stoichiometry problem on your quiz or on your final exam? Because you're gonna have to do it. All right. What other questions do we have about chapter 10? Because this is one that we covered completely remote. We took our sweet time. The only other equation is the van der Waals equation. You remember that bad boy? With A and B.
That was my least
I don't think I put it on the
I
final.
actually have like a grasp of reality on all of these except for that one. There is nothing for me.
Cool. I got 10 minutes.
I basically
Okay.
broke my will to get up in the morning.
Why did we talk about the van der Waals equation? What did it do?
Combined like
It was a corrective factor for the ideal gas law. When would we use it? For real gases. For real gas behavior outside of ideal conditions.
Is this still chapter 10 or is this chapter?
Still chapter 10. Still chapter 10. Chapter 11. Oh, you don't need to know it. You do not need to. I will not ask you to do a van der Waals equation. It had a lot of different numbers. It had an A and a B, a corrective factor. You had to plug in A and B to find P. It was a lot of work, yeah. You did them. All right, let's talk about chapter 11 really quick. Van der Waals forces. I'm just going to talk about the intermolecular forces in chapter 11.
Is that all you know?
No. That's all I have time to talk to you about. I got 9 minutes in class.
You know what? We'll just not go to the next class.
I'm sorry, no. You have to go to your next class because I have a class next.
No, I mean most of us in Lincoln.
All right.
Your next class is a final.
Your buddies with
No, my next class has a final next week, though.
I
Yes.
don't want to take up too much time, but the intermolecular forces were just with liquids, right?
Correct.
Okay.
We only talked about intermolecular forces in liquids. There were 3 van der Waals forces, and then there was the ion dipole force. This guy's the strongest of all of them. From weakest I'm going to 100% recommend you go back and you watch the video that I have made of this,
Yes, yes.
because this one's a good one to go back and watch. We go through them in detail. In order of strength. Weakest. Strongest van der Waals force. Strongest of them all. Okay? Strongest of them all.
So ion dipole isn't a van der Waals?
It is not, no. Only these 3 are the van der Waals forces. Good question.
London is the
Weakest.
weakest?
Everybody's got London.
Yeah, when did I stop having them? Like, what are the requirements?
What do you mean?
Well, like,
Everybody has a London dispersion force, always.
yeah, so like for dipole.
From there, you can add forces, right? So when we talk about intermolecular forces, don't assume that something only has one intermolecular force. Most of these things are going to have more than one, if not four, okay? You're looking for polar molecules here for dipole-dipole interactions. You're looking for these things bonded to these three molecules, looking for hydrogen bonded to these three molecules that can then only interact with those same three. Go back and watch. Yes?
So out of the Van der Waals ones, the hydrogen bonding is strongest?
Correct. Correct. Yes. That's why water is as strong as it is. Yes.
How many questions are on chapter?
On chapter 11? 4 or 5. There's 4 or 5 per chapter. There's a little bit, there might be 6 for chapter 10 and 6 for chapter 11 just because you never took a quiz over 11 or a test over 10. But you've seen all of the questions on your final exam before. Just like always. Yes?
How much do we know about liquid crystals?
That they exist. That there are 3 types. Smectic. Whatever the names of them are. You do not need to know how they orient themselves. Just, I think one of the questions that I ask is like, which of the following is not a liquid crystal?
Okay.
3 types of liquids.
What is the lowest possible amount of chapters we just studied you don't have a grade on this one?
That's on you and your grade currently. Worth 100 points? That's worth 20% of your grade? I don't know what's up.
I think I'm following up on the chapter
I'm
Say again?
like, more shaky on the-
What is
Just
the-
like what they represent. Like how to interpret one.
We should do, wait, yeah.
Critical point? Do you need me to talk about it or do you?
Oh, dude, yeah, what about that?
Got these things? What are you talking about?
The critical point's the one on the end, the critical point's the one on the right?
Yep. Like just how to interpret them? Is that what you're asking?
Well, are we just gonna be
So remember that when it comes to phase diagrams, I guess this is what I'll say, is if you're crossing something, right, you're either going from one phase to another or one phase to the other. Know the phase change names, right?
Oh, yeah. What is, can you like write them?
So this is solid, this is gas, this is liquid. When we go from solid to gas, it's deposition. Look at the diagram in your book that has the arrows that go back and forth with the names of the phases. Study those phases. Understand that a critical point, if we get out here, we've passed the critical point, we're talking supercritical fluid. And what does that mean? The phases are indistinguishable. You can't tell if it's a liquid or a gas. Okay? Otherwise, the point at which something vaporizes is the same at which it condenses, right? So the phases are opposite. It just depends which direction you're going as far as taking energy or adding energy.
And if you apply like a lot of pressure.
There's no math with phase changes on this class.
If you apply like a lot of pressure, isn't it
Jess, what's your favorite flavor of super crystal syrup?
Some of them
I like
not
cherry.
all of them, remember? There were like certain examples that say that that's not possible beyond a specific.
I don't know how they did it.
There were like
I just asked some like
example
random guy in the corner of the street for some and he gave it to me.
because of
I swear to God, I'm forgetting it.
computer with pressure on this side and then temperature.
Don't do any of that. Just study for this. That's
I have to do my part.
Once you're done, you're done.
That's it. Just
Final grades to KCC are due Monday at noon. They'll be submitted Sunday by midnight. That means that if you have something missing in the grade book, in FA Web specifically, because I just finished putting those in today, if you have something missing and it is not submitted or addressed to me directly by Sunday night, it stays missing, your grade is final. Do we understand?
Yes.
Okay.
so all the grades that are in the grade book now.
As of tomorrow morning, because she has to refresh it, right? Since I did it this
tomorrow
morning.
Is gonna be our like final grade, basically.
Correct.
Unless we have.
Unless you have something you're turning in before Sunday at midnight.
So wait.
I know know I'm good, but I'm still scared.
Anything you want to change your grade
Yes.
before it is reported has to be submitted by Sunday at
By
midnight.
Sunday.
Have
Yes.
you dropped the quiz yet or